It's my pleasure to welcome you to the CEGE CONNEXT Quarterly Lunchtime Seminar Series. This program highlights amazing and creative research that's happening in our department now, and the full realized value and impact of this work really occurs when that research is able to impact practice and policy. We began these series as an opportunity to hear from faculty as they share their perspective on recent innovations and their relevance to practitioners. We're happy to connect with you today and to highlight that the CEGE department continues to be a resource for you after you graduate. I'm pleased to introduce Dr. Jim Stagge, Assistant Professor of Civil, Environmental, and Geodetic Engineering. He is a hydrologist and engineer who integrates long-term drought records into his research to understand climate-driven precipitation patterns. And today he will provide insights into climate change, the last millennium, and Ohio. I do request that you please drop questions in the chat function at any time during the presentation. I will moderate those questions at the end of the session after Dr. Stagge's presentation. And let me welcome you, Dr. Stagge.
Thank you very much for the introduction, and thank you all for coming out on your lunch break. Let me quickly share my screen. And hide this. There we go. Like Allison said, my name's Jim Stagge. I have a focus in water resources and hydrology. And so today we're going to talk about climate change. The most typical thing that we think of when we hear climate change is changes in temperature. But my focus is really on changes in the water cycle, runoff, stream flow, precipitation, those types of things. And to kind of inform my research, I just wanted to kind of give a broad overview. So kind of my perspective on this, if we're talking about climate change, is, there we are. We have relatively few records of observed climate, temperature, or precipitation. We really only have about 100 to 120 years worth of good modern style observations. And that really represents a pretty small glimpse as to what's been going on. And a lot of that time, we assume that we've been experiencing the effects of anthropogenic climate change. And so really my goal is to contextualize the last 100 years or so of observations by looking backwards and looking forwards. So looking backwards, several hundred to potentially thousands of years, to kind of situate the last 100 years into a longer context, and then looking forward with climate models to figure out, all right, where have we been, where are we now, and where are we going? And so that's kind of my perspective on where my research fits in. And the concern now is with the effects of climate change that things that were once considered extreme, so we're going to be talking about sort of floods on the wet end and droughts on the dry end, things that were once extreme might be becoming typical, sort of the idea of this new normal. So things that would have been very unlikely to occur with our grandparents' generation and further back, we're experiencing now more often, and then thinking about our children and their children, right? We might be moving into these more challenging climate zones. So today, I'm gonna kind of as a broad perspective as to what we're gonna talk about, we're gonna start talking about proxy records. So how, and I'm gonna focus on tree rings, how we can actually look back in time to get a sense of our climate. Then actually, we're going to take a bit of a detour because I can't help myself and talk about something that's cool and it's got lots of pretty pictures. So we're going to take a detour into Ptolemaic Egypt. Then we're going to come back and we're going to talk about what the past, modern trends, and then future projections are telling us about the water cycle and what that means for the state of Ohio. All right, so I already used the word proxy record, but I really need to define this. So proxy records are anything that sort of stand in for instrumental records. We can think of this as being sort of natural thermometers. So obviously we weren't measuring temperature to a very exact level hundreds of thousands of years ago, likewise with precipitation, but we can use many of these different proxies to approximate what we think was going on. And so what we see here on the left, these are written records. We'll talk about how those can help to inform us. We've got soil cores that can tell us something about what was going on with the climate. Those of you that are familiar with the Byrd Polar and Climate Center, they have a huge repository of ice cores, which is what you see one step over to the right. These trap little bubbles of air. And so if we can go in and extract those bubbles of air, we get kind of a snapshot of what climate looked like if we can collect these ice cores. And then finally, on the end, tree rings, which is where most of my work is going to be talking about. With that said, I promised a detour. And so we're actually going to zoom out and then we can get back to Ohio, which is some additional research that I've been working on, talking about, and the connection here is that this is another climate catastrophe, but that affected the Egyptian society of Ptolemaic Egypt about 2,000 years ago, between about 300 to 0 BCE. I'm rounding. And to do this, rather than using tree rings, we're instead using written records. So we still have papyri that tell us about what was going on in the society at the time. They note things like it was very dry, we got a poor harvest. They note things like revolts and economic instability. And then we're also using ice cores, which tell us that there were 4 really large volcanic eruptions in the 11-year span from about 168 to 158 BCE. Those volcanic eruptions, we've got good modeling that tells us that they would have disrupted rainfall across a lot of the watershed. And we're trying to look at, to make that connection between these large volcanic eruptions and how they affected society. So a little bit of background to go into how we can get these things. This is a papyrus that I was able to see. It's at the Yale Peabody Museum there in Connecticut. This is Ptolemaic era. And the exciting thing about these papyri is that they're on the back of what are essentially mummies. Now, by the time we got into the Ptolemaic era, they weren't building these large sarcophagus structures. Instead, they were using what is essentially paper mache to create masks and these chess pieces. The exciting thing is that when these things disintegrate, so this is an example of a really nice looking, well-preserved one, but when they disintegrate, we find that on the back of all of this paper mache are notes, letters, all of this contemporaneous information of people sending notes to one another saying, we had a really bad harvest, send help, or, it's basically their waste paper bin that's come down to us because it was on the back of these, what's called cartonnage, these masks. So a really interesting way that we can get this snapshot. Imagine just getting a few newspaper clippings of our society 2,000 years from now, whatever's in your waste paper bin. To give you some context, the part of the Nile that I'm going to be focusing on is what is essentially Egypt now. The interesting thing here is that the Egyptian Nile goes through 2 periods of wet season and a dry season, and that's mainly driven by rainfall. Let's see if my mouse can work here. Up here in what's called the Blue Nile, what's now mostly Ethiopia. And then the base flow that's coming from this gray area is the White Nile, and you can see that's pretty constant throughout the year. And by the time we get to the Egyptian border, that's kind of shown by this red line, basically all the water that's going to be in the river is already in there. There's very little rainfall in Egypt, which is great for us because it allows us to model this stretch of Egypt as basically inflow and outflow. And the annual flood is directly tied to the way that they ran their agriculture. Every year the Nile would flood and it would inundate some area, and then they would plant that for the next year. So my group then so we're kind of mixing modern and ancient information. We're taking remotely sensed elevation data from satellites, modern hydraulic techniques, HEC-RAS, a two-dimensional model of the entire Egyptian Nile, and this side channel that's called the Bar Yusuf. There's about a million calculation cells, so each one of these is performing some hydraulic calculations, and we hit it with a simulated flood. And we hit it with a bad flood year and a good flood year. We're also being informed by observations, surveys that took place around 1900. So we're trying to approximate what the Nile would have looked like 2,000 years ago when it was near natural, as opposed to what it is now with all of the dams and so on. And so again, I just am excited. I'd like to show some pretty pictures. So here's an animation of one of these flood years, and in what's called the Cana Bend. So this kind of bend, water's moving from the bottom to the top, and you can see the flood wave propagates out, it fills up the river channel, it floods out into the floodplain. Now we can let all that water infiltrate into the ground, evaporate, and then plant. And so by simulating a poor flood year and a good flood year, we can try to see how much area could the Ptolemaic Egyptians have reasonably been able to cultivate in any given year. We feel pretty confident about this model. Let me stop that from running. We feel pretty confident about this model. These are locations of towns that we know, towns and buildings and monuments and things that we know were there 2,000 years ago. And the exciting thing is, when we simulate these floods, we see these towns sitting up top, up on high ground with flood waters all around us. And we have contemporaneous documentation that says this is exactly how things worked. So we feel really confident that our model is more or less replicating the way that the Nile would have flooded this area. And then we can use that to say, during a really bad drought year, we see huge areas that go basically not inundated. So there would be no possibility for agriculture in a lot of these areas because the Nile isn't getting up and out of its channel. As opposed to a typical year where all of this area would have been inundated, irrigated, and the community would have been able to plant and harvest. And the exciting thing, or the interesting thing maybe, is what we're seeing, this area is called the Thebaid. All of these dots here are what was at the time Thebes, which is located up here around this bend. What we find is this series of revolts that lined up with this volcanic eruption that would have depressed the Nile flood. So we would have had really bad flood years for several years in a row. And the places that seem most affected are these kind of upstream areas in green. This is exactly where all the revolts started. So we actually had a coup in this part of Egypt, and the revolt started working its way downstream. This is also kind of as far as possible as you can get from Alexandria, which was the capital of the Ptolemaics. And so we've got all of these records, written records, to say send troops up to fight this. And we think it was because they had this extraordinary climate catastrophe where they had many bad years in a row famine and really poor agricultural harvests. So that's my sidetrack. We can get back to what we actually wanted to talk about today, which is talking about more modern proxies. And for that, I'm going to use tree rings. So here we are. Here's an example of a tree ring. The whole reason why tree rings can operate as a proxy, basically a natural stand-in for measuring temperature or precipitation, is that, at least in temperate climates, we have this annual cycle of growth and senescence. Basically, not always the leaves fall off, but basically growth stops during the winter, and then we have a growth period. And each one of these annual growth periods will put on new tree rings, we'll get new growth in the tree, and then we'll have senescence, and that will create layers that are annual that correspond to each year. And so we can go in, and again, this is all assuming, and we'll talk about this in a moment, if we choose the trees correctly, if we're in a good place to make this connection to some measured climate variable, then we can get something out of it. So as an example, here's the year 1700 that someone has gone in and dotted each 10 years to show each one of these rings. And we can see big variation, well, reasonably large variation, visible variations in how thick each one of these rings are, and that might tell us something about the climate in each one of these years. I get this question a lot, so the question is, do you have to cut down the tree? Do you have to take these really destructive samples? Do you have to take these huge samples? So in some cases, we can use a full cross-section of a live or a dead tree. Obviously, the live tree would have to be cut down. But more often than not, we're using what's called an increment borer, where we basically bore into the side of a tree. This is a felled tree, but we bore into the side of this, and then we only have to extract this little sample that comes out of the center of this borer, and that'll give us a sense of each one of these rings. We then collect, so we don't want to rely on just a single tree at a single site. We want lots of shared signal. So we generally want to take at least 2 samples per tree, just in case maybe one side was getting more light or grew strangely or something was going on. Right? We want a few samples per tree, and then we want something like 30 or 40 trees in a single location. The idea being that if all of those trees show a really poor growth year, then we can assume that that is actually a climate signal, as opposed to, if one tree has a poor growth, that could be, an insect infestation or something odd that happened to that particular tree. But if we get this signal spread out across lots of trees, then we can be pretty sure that something was going on in that year. We take this sample back into the lab, prepare it, and can measure with a microscope the width of each one of these rings. And of course, we've got a few key species that work well, and the rings show up slightly differently, and they show up, and they measure slightly different things. They're sensitive to slightly different things. So here we are, bald cypress, which is kind of an interesting tree. It's almost a swamp tree. It tends to be very wet, which is going to operate very differently from things like red cedar or pine. All right, so we then take all of these samples at a given location and we put them all together to create what's called a chronology. So some of these trees might still be live, so they end at our current time. We can also line up dead trees, and if we can sort of, let's see if I can get my hands in properly, if we can sort of ladder our way backwards, then we can line up when we think that tree would have died. And if all of the rings line up, then we can go back even farther than any living tree. And that's how we create these long chronologies. Now, depending on what we want to measure, we can choose where and what trees to sample. So in general, what I'm going to be talking about when we're trying to measure rainfall or soil moisture, we tend to want to find places where trees are very sensitive to water. So that means we don't want to get them right next to a river where their roots are always going to be in the water. They'll always be happy. They'll never show really any variation. We want to get trees where they're really being challenged, so maybe on a slope or in poor soil or in an arid location. And in that way, their growth is very much isolated to the effect of how much water they have. That stands in contrast to if we wanted to reconstruct temperature, we oftentimes are looking for cold locations. So northern elevations or northern latitudes or really high elevations. Because there, it's not that water is the limiting factor, it's temperature. So depending on how long the growth season is, so how quickly we get out of the frozen conditions and we can start growing, that tells us how much the tree is going to grow, and that tends to be linked with temperature. So again, assuming we choose our tree just right, or a set of trees just right, and we create this chronology, and all of the trees agree that a given year was a really poor growth year, and a given year was a really good growth year, we can then line that up with observations over the last 100 years and check and see how well does this annual growth in a tree line up with something like precipitation or soil moisture. And we do a lot of checking because we're going to be extrapolating this backwards in time, so we want to make sure that we're not sort of overfitting this relationship. But once we have a good fit, then we can go back in time as far as we have enough tree ring chronologies, and as far back as we feel confident that this relationship will hold. So just to give you a sense, this is about 10 years old, but and very much Northern Hemisphere focused. But this gives you a sense of where our tree rings are, or at least where they were 10 years ago. And you can see kind of a big grouping around the US. We're kind of very lucky in terms of how many tree chronologies. We've got really great coverage in North America. You can also see kind of a ring around the higher latitudes and along, for example, the Himalayas and some other high elevation places in the Alps, although that's kind of hard to pick out. Those tend to be our temperature chronologies. We tend to have kind of a missing band through the tropics because in a lot of places, right, the tropics aren't experiencing this growth or they aren't experiencing as extreme the growth and senescence period. If there's always plenty of water and there's not this big senescence period, then we don't get this annual cycle that gives us good tree rings. That's not always the case. Some colleagues are doing some really interesting things in Southeast Asia, trying to get around this. And we do, of course, have tree rings that are in the Southern Hemisphere, just much fewer. So we can do really exciting things with this. Again, I was showing you what we think was going on in Ptolemaic Egypt. We can also take a look at what we think was going on in the US or the proto-US. So the colonies of Roanoke and Jamestown. And what we find, and this is others' work, when we do a reconstruction of summer, what is essentially precipitation, is that both of these colonies were set up during periods of really extreme drought. And so just out of pure dumb luck, bad luck, we know that the Roanoke colony failed. This may have had something to do with it. You know, you can pick your favorite year and look back and try to think of what was going on at that time. All right, so that's kind of tree rings and precipitation reconstructions kind of in a nutshell, the very dime store tour. Just to show one more thing, which is that if we, rather than reconstructing at a single location, if we're very careful and make some assumptions and have this good coverage, like we do in North America, of tree rings across the entire continent, then we can start to build out what's called gridded reconstructions. So rather than reconstructing precipitation or flow at a given site, we can try to get a sense of relative precipitation across the entire continent. And so we start to see some spatial patterns. Of course, this only works where we have really good coverage of tree rings, and even then, as we start to get to the edges of these reconstructions, right, our confidence starts to go down a little bit. But these are some examples of these, what are called drought atlases. All right, so we've got all the background. Let's talk about what this means for Ohio. So now we're getting into my work. Over the last 5 years or so, myself and my graduate students have been working to build out statistical models that can merge the last 100 years or so of observations with these gridded reconstructions based on tree rings. And then we also have climate models that have simulated the last 100 years or so, and then with this sort of historical period. And then we also have, for a few climate models, we have runs what are called the past 1,000 years. So that covers us back to 850 CE. And that's not as exact as our tree rings, but they should be forced by things like volcanoes and atmospheric gases and things like that. And then we can also look into the future with these same climate models to create this continuous range. And so kind of merging these three different data types is difficult, but it allows us to kind of lean on the good things, so we're very confident in our observations. The tree rings, we feel very confident at this annual scale. They are exactly what we think happened in a given year, and the climate models give us kind of a more continuous estimate of what we think physics should tell us about what's going on in the climate. So we combine all of these. I'm not going to bore you with all the stats. And we can do things like the following, which is look at trends in drought relative to 1850. We use 1850 as kind of our definition of what we call pre-industrial conditions. So this is when we really started adding a lot of greenhouse gases. And so all of our climate change models use this as kind of a threshold. And what we see here is that since this 1850 kind of break point, we've seen our dry years, so our driest years have gotten drier, particularly for the southern part of North America, especially Mexico and the Southwest. But then by the time we push into the summer, this threshold pushes further north, and it starts to include places like Ohio. And if we push this into the future, what we see is not a kind of reversal. What we see is an intensification. I should be clear here, the dots that I'm showing here, dots represent a not statistically significant trend. So everywhere where you see pure color with no dots, that's where we're pretty confident that this trend exists, and it exists well beyond what you would expect kind of from random chance. And so we see the same thing, this pushing up during the summer to include parts of Ohio and most of the US. So our driest summers are projected to get worse. And For the Southwest and particularly Mexico, this is basically everything is getting drier. We can also look at the wet years. So the wettest years, and I'm just going to focus on the spring because this is where we see the strongest signal. What we see here is that since 1850, we've seen a general wetting trend for spring across most of the US, except for the Southwest and Mexico. I should say across most of North America, Mexico, and the Southwest of the US. And as we push into the future, this is projected to intensify. And you can see it's very strong across the Northeast and up into Canada. And so if we were to put all of this together, first, the fact that we're seeing not a reversal, the fact that we're seeing these trends continue, so we're taking observations and then we're also seeing them in all of our models looking forward, we feel pretty confident that this is the signal of greenhouse gases, anthropogenic climate change. And if we had to simplify the message down to just a few kind of zones, what we're expecting to see is basically a wetter Northeast across most of the year, a drier Southwest and Mexico. And then for most of us that live in the center, we're going to be kind of pulled in both directions, where we're going to see wetter winters and springs and drier summers. And for those of you who are living in Ohio, if you think back to last year was a perfect kind of poster child for this behavior. So again, I know it's almost a year ago, but I just wanted to show you where we were about this time last year, which is on the left. So coming out of winter into early spring, we were about 1 to 2 standard deviations wetter than normal. So we were basically extremely wet. All the rivers were really high. We were worried that things were getting far too wet. By the time we flipped over into late summer, we were experiencing one of the worst droughts that we had on record. And so this rapid shift, this kind of whiplash effect from wetter than normal to drier than normal in the same year is more or less what we're projecting for a lot of the center of the US. And I promised a zoomed out view. So just to, again, try to make this point of how extreme some of these trends can be relative to what we've experienced. This is an example. So I'm just zooming in on that Southwest, the lower Colorado River. So that includes a lot of Arizona, bits of Nevada, bits of Southern California, all the way to the east. And if you look on the left, this is showing our kind of time series of this measure of wetness, what we call the SPI. And you can see, right, there's natural fluctuations because there are natural climate variability, or there is natural climate variability. What we see there at 1850, that first dotted line is kind of our threshold point where everything is relative to this. So anything that's in the blue is wetter than normal. Anything in the red is drier than this 1850. And you can see we've had this dramatic shift to the modern period, which is that second dotted line, and we're projected to shift even drier into the future. And what this means in terms of the distribution, you can see here, these are the last 1,000 years or so of these distributions of precipitation, and you can see that last from 1800 to 2000, this dramatic shift to the left that we've never seen previous. So this gives us pretty good confidence that what we're experiencing stands out apart from natural variability. And of course, we're all interested in what's going on in Ohio. So I'm zooming in on that winter part of the year where we think that things are getting wetter. And the same thing here, although less extreme. The southwest of the US is one of our more clear signals. The Ohio signal is a little less clear, but we do see a kind of a dip in the mid 1900s that would have lined up roughly with the Dust Bowl. And then since then, we've seen a dramatic increase that's projected to intensify. So again, putting all of this together, the things, if you could take away anything, which is kind of a wetter north, drier south, and all of us stuck in the middle are going to become more variable and more of these sort of whiplash years. And 2024 would be a good example of what this would have looked like. And then the last thing is that we see agreement among the models and observations. We see this signal standing out against natural climate variability, which gives us a lot more confidence that this is human caused and due to greenhouse gases. And then I just wanted to take the last 10 minutes or so, because I want to leave plenty of time for questions, to kind of zoom out and also talk about so we've been talking about precipitation. What does this mean for things like extreme rainfall or for stream flow? Those of you in the Columbus area, you can see this is, what is this, Creekside over in Gahanna. You can see the flooding is just up to our protection. This normally would be a trail that you can see kind of the bridge here. And this is from last year. So, unfortunately, for us here in Ohio, at least the last round of the previous generation of climate models were showing that the kind of frequency, the likelihood of these really large storm events in the future are projected to intensify, and it really is a bullseye painted right on the state of Ohio and West Virginia. What this means is that where previously 1850, 1900s, the types of storms that we would have expected about every 20 years, we can now expect to see about every 5 years. So that's a pretty strong intensification. And you don't have to take the model's word for it when we look at the observations. So this is really exciting work that was being done by an undergraduate student, Sophia. She showed that using our observations of these 24-hour maximum precipitation, we see everywhere that you see a blue dot here is an increase over the last 100 to 120 years. And so yeah, it's a little more noisy because this is the real world as opposed to a model. But in general, we're seeing the same pattern that the models are predicting, which is an intensification of these extreme rainfall events. And we do have a good theory as to why this is happening. So because of what's called the Clausius-Clapeyron equation, we don't need to know that. The analogy that I like to use is that the atmosphere is like a sponge. So of course, water is cycling through, so it rains, it lands on the ground, it infiltrates, works its way into oceans where it evaporates, goes back into the atmosphere, and the cycle continues. For every increase in temperature, you can imagine that sponge, which is the atmosphere, increasing in size or capacity. Because there's more carrying capacity in warmer air. And so what that means is we're essentially supercharging the water cycle. We can suck more water up, so the drier parts can get drier. We can hold more water as water vapor in the atmosphere, and then when we do release it, we're going to release a lot more. And so there is some physics behind why we expect with warming temperatures to see more extreme hydrologic events. And then, of course, what oftentimes matters is how does this work its way down into stream behavior or rivers. And so some work from about 10 years ago from others showing increases in flood magnitudes that are kind of right at this border between the state of Ohio and Indiana. We see this kind of bullseye again. So what this is showing is an increase in the magnitude of large floods. And work that's being done by my very talented master's student, Connor O'Keefe, on the right-hand side, kind of updated with slightly different methodology. But again, we're seeing the same thing. The kind of eastern Indiana, central Ohio are showing these increases in really large runoff events. And the concern is that this increase in large runoff events is then going to push more sediment and nutrients into things like the Lake Erie, which can cause eutrophication, algal blooms. And not only that, but of course flooding. The one thing that we haven't talked about yet, which I can kind of end here, which is something that we're trying to build out, something that we've seen in the data, and we don't think that anyone else has really picked up on, something that we're pushing to kind of fund and do more research in the future, is that we see this consistent pattern of these large events occurring earlier in the year. So things that would have occurred in mid-March are now occurring in late February. And all the dots that you see here in blue, basically again on this Ohio-Indiana border, are places where we've moved about a month earlier in the season. And so again, same concern, if these rainfall events, if these large runoff events are happening earlier in the year, they might be landing on, they may be bringing with them more nutrients and then letting them sit in, for example, Lake Erie. By having these things happen earlier in the year, now we've got a longer, kind of drier summer, which again can cause these algal blooms. So again, very preliminary work, but direction that we're moving into. And we think this is probably dependent on temperature. So again, just to bring these things all around, why does this matter? This year, in fact, a month ago or so, the governor signed a $10 million bill. Again, because of the severe drought last year, we were seeing water supply drops last year because of this drought. And then there's this concern that the combination of drier summers, wetter winters means more fuel for these harmful algal blooms and longer, hotter, drier summers to create the conditions that causes them. So I guess I'll leave you with maybe not the most fun takeaways, but those are, climate change is real and we should be considering it in our planning. And if you had to take nothing away from this, what we would expect for Ohio is kind of this wetter winter and early spring, followed by drier summers, and an increase in the intensity of extreme rainfall and the runoff that it creates, and likely happening earlier in the season. And then if we're talking about climate change, we should be talking about ways to address it. And there's basically two ways. The first through mitigation, so trying to decrease greenhouse gas emissions. It takes a few decades for the effects of greenhouse gas emissions to sort of show up as a climate signal. It's like trying to turn a large ship. So we're essentially paying for the sins of the previous generation. And when I tell this to my students, they say, okay, so we can blame our parents. Sure, if you want. The idea is that we should be taking action now because it's going to affect younger generations and the future. And doing things like pulling out of the Paris Climate Accords are going to hurt the younger generation and the next generation. So if we are going to be pulling out of agreements like that and not doing work on the mitigation side, then we need to think about adaptation So in some cases, this climate change is already kind of written, and it's going to happen because of previous greenhouse gas emissions. And we should be thinking about how we can change our management and engineering structures to make sure that even though they were designed based on a climate that was sort of typical 30 or 40 or 50 years ago, is it going to be up to snuff moving forward? And so with that, I'm sorry to end on a downer, but I did show pretty pictures from Egypt. So, take that with a grain of salt. I just wanted to thank, wanted to thank all of you for coming out to the talk, all of my funding sources, and everybody that helped to do my research group that's helped with a lot of this research, and of course, Bird Polar, that's been a great resource as well. And with that, I think I've left enough time to have some questions.
Thank you, Jim. So yeah, I encourage folks to put questions in the chat if you'd like. There's already one queued up. I'm happy to read it, Jim, or if you're able to access that through all of the Zoom interface that seems to change on a regular basis. And, I think also too, we're a fairly small group today. So I really want to thank those of you who have joined us that the raise hand function, I think, can also work too.
So yeah, I can see the question. I'm just reading, and thank you, Stuart, for your comment. Oh, that's exciting that you were in the. We have an archaeologist that was working in the Delta. I should point out that all of these models totally break down in the Delta because it's what's there now likely doesn't look anything like what it did back then. But we feel pretty confident that the main channel where we're focusing kind of upstream should be pretty stable. But his question is, do you think we'll need to consider water storage and irrigation beyond what is typical? I'm surrounded by farm fields, no access to river stream sourcing, wondering how these farmers will manage their crops, drought-resistant seed engineering may become. Yeah, so the question, if I can summarize it, and Stuart, please check me if I say something wrong, is, or my interpretation of the question, I guess, which is, in the western part of the US, we have really strong infrastructure for irrigation. We use up a lot of water, groundwater, and we move water around through channels for irrigation purposes. Here in Ohio, we haven't built out that infrastructure because we, for the most part, haven't needed to. We've kind of been blessed with plenty of water. Do I think that we'll need to be moving towards some of these storage or irrigation solutions? We may. So I will admit that agriculture is not my forte. I will say that it could help to balance some of this. I think we have to balance the cost versus benefit. So these bits of infrastructure can be quite costly and require a lot of agreement across a lot of people. So probably kind of smaller and more distributed solutions might be better, whether that's changing the crops that we're growing. In some cases, trying to we can do things like paying in certain years to support farmers through bad years, letting their crops go fallow, which I know is a hard thing to do for a given dry year, so that they're ready to plant again for the next year and they're not economically struggling. And then potentially drought-resistant seeds. Certainly that's an option, and that's well beyond my expertise, so I don't want to speak to get over my skis on that one too far. But yeah, we should be considering all of these options. And my goal is to sort of provide the input for those that are in more in the agricultural spaces that can be thinking about how we might address these problems. This feels like my class. Nobody wants to raise their hand.
Well, I will ask a question. And to what extent has some of your research findings begun to get translated into the policy space?
Yeah. So a lot of what I've shown today has been kind of things that have been published very recently. So a lot of this hasn't quite made it down into the policy space, but I will say that previous work that's a little bit older has now started working its way into places. You can kind of see the path of where I was previously. So the Potomac River Basin, the group that manages their water is called the ICPRB, the Interstate Commission on the Potomac River Basin. They've been very supportive. Max's name is on here. Max Torbenson and I created a reconstruction of flow on the Potomac River, which was very fun because then we could look back, we could pick a year and we could see that, I think it was Thomas Jefferson had written something about a bad crop year. So it's always fun to get validation from Thomas Jefferson. I can't remember if it was Jefferson or Washington, but it was someone who was commenting. But my point being that some of these hydrologic models and climate simulations has informed how they've been adjusting their policy to address drought and water management for the Potomac River, which controls water in Washington, D.C. And likewise, the whole reason I got started with tree rings was my work in Utah, where water is extremely crucial. It's kind of the lifeblood of their agriculture, and they're very aware of, the farmers there are very aware of a changing and drying climate, and they've started to implement changes in how they manage their water, thanks to some of this tree ring work. Oh, great. Caleb's question. Implications for how we design and operate stormwater and wastewater systems. So I'll tackle stormwater first, which is to say that based on what we're seeing here, we need to consider climate change when we design infrastructure like stormwater pipes or collection systems or detention basins, if we think those are going to be functional for decades. And so the latest guidance on how we design or how we choose the design storms has included kind of a long-term trend analysis component of it, so that we're not designing kind of the detention basins of today, we're designing them for some future event with potentially more intense rainfall. And so we are starting to consider these changes, and it is starting to trickle down into our design process of potentially sizing things differently. And you've seen it kind of work its way into, if you're in Columbus, kind of the idea of Blueprint Columbus, which is where we're trying to prevent combined sewer overflows. So where when it's raining really hard, we get a mixture of stormwater and wastewater that's being discharged into our rivers because it overwhelms the system. Some of that is motivated by potential future increases in intensity and trying to mitigate that so that we don't see an increase in these combined sewer overflow events. That was a long way to say that we're starting to have to think about making things bigger. And the timing thing, just to go off on a bit of a tangent, the timing issue that we're seeing, that our events, our large events seem to be occurring earlier in the season, might need to impact how we manage our reservoirs. So we might need to be catching more water earlier in the year and releasing it later in the year. Can I speak to erosion control measures beyond those currently implemented that may be required given the forecasted trend in earlier and more intense runoff? Interesting. Again, I don't want to overspeak. I think most of our erosion control measures are going to still be valid as we move into the future. I think this just emphasizes the importance of those. And we might have to, well, no, it's not really erosion control, it's more sediment control. I was going to say we might have to build out larger sediment forebays during construction, things like that, to deal with more intense rainfall. But I think the erosion control measures that we have now are still going to be valid. We just might need to think about where we're putting them, adding more, those types of things. And then just to build off of that, to say that not all is lost. Just know that it's not, there's a whole group of people that are thinking about these types of questions and how we can build for the future in terms of stormwater design or erosion control. Thanks, Alan.
As we're moving to the end of our hour, I would like to thank you again, Jim, for being able to spend some time with us today and take what I know to be a super complex set of calculations and integrated models, and really distill that down into some key graphics and some very clear explanations of your methodologies, your processes, and certainly these very important implications. And really enjoyed the historical tour along the way. So thank you. And I remind everybody that we will have another seminar on March the 5th, so just 1 month from today. Dr. Kelsey Best will be talking about some of her work, looking at some of the questions of adaptation around climate change, as she's been examining how isolation of communities because of sea level rise before communities get inundated on the coast may be leading to some implications with respect to climate justice. So I hope you'll be able to join us again. And just a reminder that those of you who requested CPD certificates, those will be to you and available in the next 2 weeks. So thank you so much for joining us today.